Welcome to section 2.2, limit of a function and limit laws. So the plan is to take our lead from the previous section where we were estimating tangent lines to a curve and use that really motivationally to look at this idea of a limit. Now, the idea of a limit is fundamental to everything in calculus. This Calculus 1 class is about limits, derivatives, and integrals. Derivatives are a kind of limit, and integrals are a kind of limit. In Calculus 2, you'll do more, maybe some more derivatives, definitely more integrals, and you'll do something called sequences and series. And sequences and series are both limits as well. In Calculus 3, you'll deal with a lot of these same topics, but in higher dimensions. We'll stick with functions of a single variable in the xy plane in here. But you'll see multiple integrals, for example, defined in Calculus 3, defined as limits. So without limits, there is no calculus. But this is an extremely complicated idea. So the plan in this section is to give you a feeling for what a limit is. We'll look at things in a non-rigorous way. I'll try to be respectful, though, to the underlying rigorous math. So plan is, I'm going to follow the textbook, Thomas's Calculus, but I'm going to be super careful, probably even a little bit more than Thomas's Calculus is, in respecting the math. All right, so let's start with looking at functions. One must be very, very careful when looking at an equality of functions. Consider the following. Let f of x be the function defined as given here. A bad place for a new line, but f of x equals x plus 1 times x minus 1 divided by x minus 1. And the function h of x equals x plus 1. Now, these ain't the same functions. They don't even have the same domains. The domain of h of x is all real numbers. The domain of f of x is, we got to throw 1 out. All real numbers except for x equals 1. So they don't have the same domains, they're different functions. Now they're awfully similar, but they're not the same function because there's places where one of them does one thing and one of them does another. At x equals 1, h of x takes on the value 2. At x equals 1, the function f of x, it ain't even defined. And there's the problem, that division by 0 that would result if you plugged in x equals 1. So we can't say this. So I'm very hesitant to write down something that's false. It's very subtly false, though. Well, limits are a subtle idea. You can't say x plus 1 times x minus 1 over x minus 1 equals x plus 1, full stop. That's false. Saying something like that, the implication would be that for all real numbers x, that equation holds. Well, it doesn't hold for x equals 1. You can't just cancel these x minus 1s and walk away. It's more involved than that. If I cancel the x minus 1s, then I get x plus 1, and I've actually lost the information that I can't use x equals 1 on the left-hand side. So here's the problem. As long as x isn't 1, they're the same. So they're not the same everywhere. They're not the same at x equals 1. Okay, how about we write that down? We can say the following is true. That if you'll take that quotient, you can cancel the x minus 1s if x is not 1. And say these two quantities are equal with the disclaimer, the caveat, that x is not equal to 1. If x equals 1, they ain't the same. The one on the left isn't even defined. This isn't defined when x equals 1. If x is not 1, that denominator is not 0. I don't know what number you're getting out, unless you'll tell me what x value you're using, but it's the same as this x value up here. And we can cancel x minus 1 and x minus 1 if we didn't lose information, if x is not equal to 1. That information being 1's not in the domain of this function. So I've verbally written out that that equality holds if, bold-faced if, x is not equal to 1. We could look at the graphs of the functions. Here's the graph of the h of x function. H of x equals x plus 1. Piece of cake. Straight line. Y-intercept is 1. X-intercept is -1. 2 points determine a line. It's got slope 1. However you deal with graphing lines, there you go. So there's the h of x function. Notice at 1, it takes on the value 2 because 1 plus 1 equals 2. And here's the f of x function. All right, well, the f of x function, it's doing the same thing the h of x function is if x is not equal to 1. So we get the same straight line as we get over here if x is not equal to 1. What happens at 1? Well, the h of x function takes on the value 2, and the f of x function is undefined. Not defined will poke a little hole in the graph at that point. So here's the graphs of those two functions. I told you they were different functions. They got different graphs. Okay, the graphs are really similar, and the only place they're different is at x equals 1. All right, so that's why we can get away with this claim up here. We've got the same function provided x is not equal to 1. Okay. We want to talk about the behavior of the f of x function as defined here for x near, quote unquote, near 1, but not equal to 1. Okay, so all the interesting stuff seems to relate to an input value of 1 or input values near 1 is where we're going with this. Okay, well, if it's not equal to 1, if the input values are not equal to 1, the x values are not equal to 1, I can replace the f function with the h function, as long as we know x is not equal to 1. That was the conversation from the previous page. So we got the same functions, f and h are the same functions for x not equal to 1. So if you'll consider x values near 1, but not equal to 1, whatever near means, it's part of the problem here. Whatever f does, h does the same thing, same behavior. If we stay away from 1. At 1, it's a different story. We're not having a conversation about what happens at 1. We're having a conversation about x values that are near 1, but not equal to 1. Okay. Then what happens to the h of x function when x is really close to 1, but not equal to 1? The h of x function, let's go look at the graph. Just happen to have it right here. If I input x values close to 1 and less than 1, we get points on this curve where the arrow is. Don't plug in 1. I don't care what happens at 1. Plug in some more x values close to 1, but greater than 1. Okay, that corresponds to points along the curve here. The y values in either case are bracketing around 2. I didn't use 1, I used numbers close to 1, whatever close to means. Okay, well, the h of x function, it gets close to 2. If the input values are really close to 1, then the output values are really close to 2. If the input values are really, really close to 1, then the output values are really, really close to 2. It's this really, really close to stuff that we've got to put a clean definition on. Well, then if h of x gets really close to 2, then so does f of x for such x values, because h and f are the same functions as long as we stay away from 1, and we did. We talked about input values close to 1, not at 1. Doesn't matter what happens at 1. The only difference is what happens at 1 in terms of the functions. One of them is 2, and the other one, it ain't defined. F isn't defined at x equals 1, h of 1 equals 2. We want to say, and this is my wording here, this you won't find in the textbook. I want to say that f is trying to equal 2 at x equals 1. This closeness idea is what I'm trying to motivate. All right, so let's look at an informal definition of limit. I prefer to keep it mostly in terms of looking at graphs of functions at this stage, but let's get this informal definition out in the open. One quick comment. Anybody ever ask you to state the definition of limit? This ain't it. We'll have the definition, the formal definition of limit, in the next section, in section 2.3. The informal definition of limit deals with this close to stuff. If f of x, or let f of x be defined on an open interval containing value c, except possibly at c itself. Okay, let's stop and talk about that. Open interval containing c, except possibly c itself. So if I choose numbers close to c and a little bit bigger than c, the function's defined there. If I choose x values close to c and a little bit less than c, the function's defined there. This first sentence is simply saying the function's defined close to c. Except possibly at c itself. Boldfacing this, in all this limit stuff, it doesn't matter what happens at certain points. In this case, at point C. It doesn't matter what happens at point C. This function may not even be defined at point C. Doesn't matter. We're talking about limits. And limits aren't affected by what happens at points, at specific points. It's this whole close to thing. If it were only as easy as plugging in numbers, we'd be good to go and we wouldn't have to have this long conversation. Under that setting, if f of x gets arbitrarily close to L for x values, input values, sufficiently close to value c but not equal to c, we say that f approaches the limit L as x approaches c, and this is what we write. This, you'll be seeing a lot of this in the next 3 calculus classes. All right, so here's the symbols for limit. It's read, the limit as x approaches c of f of x equals L. That's how you'd read those symbols. Why is this informal? Well, the words are not very mathematically clean. What do you mean by arbitrarily close? What do you mean by sufficiently close? And we're going to spend a bunch of time trying to explain what that really means. So this is an informal definition. It's not mathematically rigorous because those ideas of sufficiently close and arbitrarily close, they're not defined. We'll define them in the next section. Believe me, it's worth going through this motivational stuff or this informal stuff before we get to the more complicated formal definitions. Okay, so let's look at this limit again. Limit as x approaches 1 of f of x equals the limit as x approaches 1 of, here's what we took for the f of x function as described before. What's that limit equal? Evaluate that limit. Well, as we saw before, we can say this, provided we put the disclaimer down, you can cancel those x minus 1s as long as you know x is not equal to 1. So I'll just put it in writing. I'm saying this equality holds if x is not equal to 1, because it doesn't hold when x equals 1, as described above. All right, so we could say the limit as x approaches 1 of f of x, this particular function here, is the limit as x approaches 1 of x plus 1 if x is not equal to 1. So if I put the disclaimer in, I'm okay with making the substitution for the f of x function, substitute the h of x function in the symbols we had initially. So yeah, I can cancel the x minus 1s as long as I write down, well, it's understood this equality only works when x isn't equal to 1. So in words, this limit question is, what does x plus 1 get close to when x gets close to 1, but not equal to 1? Oh, good thing it's not equal to because of the highlighted comment there. Well, x plus 1, when the x value is close to 1, x plus 1's close to 2. How close to 2 would you like to get? This is what the arbitrarily and sufficiently close stuff is. Let's play that game for a second. Finishing my thought. The limit as x approaches 1 of f of x. This limit is the same as that limit. Something about x not equaling 1. We'll clean this up. We'll say short and in a few minutes. The limits are the same even though the functions are different because I don't care what happens at 1. That's a property of limits. I don't care what happens at 1. I care what happens close to 1. That's why it's so hard to explain. So these limits are the same. X plus 1, when x is close to 1, this gets close to 2. Funny thing, we're not allowing x to equal 1. It's still highlighted up here. The important thing isn't what happens at 1. In fact, that's totally irrelevant, as we'll see. What matters is when x is close to 1. When x is close to 1, we can make that function close to 2. All right, so, well, let's make this statement as well. The limits are the same even though the functions are different. That's the real punchline and what we're getting at here. Yeah, but they're very, very subtly different. The only place they're different is at x equals 1. And I don't care what happens at x equals 1. I'm computing a limit, and limits don't matter. It's not affected by what happens at a particular point. Now, about this arbitrarily and sufficiently close, let's run back and look at that one more time, even though it was informal. That's what made it informal, was those terms. F of x gets arbitrarily close to L. Okay, so here we were trying to get f of x close to 2. How close to 2 would you like to get? And this is how the interplay of arbitrarily close and sufficiently close works. You tell me how close you want to get. You can choose anything other than 0. You choose any little distance, little positive distance, and I'll give you a sufficiently close, that is, I'll tell you how close x needs to be to c so that f of x is within the distance you made up of L. So it's kind of a game. You tell me how close you want to get. You give me any positive distance. Then I'll find a second distance. We got 2 distances because we got x values and y values, input values and output values for a function. I'll tell you a distance such that if you'll make x my distance within my distance of c, then f of x will be within your distance of L. And when we state the formal definition, that's precisely the logic. So down here, this one's a little misleadingly simple, it turns out. I'd ask the question, how close do you want x plus 1 to be from 2? You want it to be within 1/10? Then I say, let's make x within 1/10 of 1. So x would be between 0.9 and 1.1. When you add 1 to it, you'd have something between 1.9 and 2.1. You'd have something within 1/10 of 2. You want to make x plus 1 within 1/1,000,000th of 2? Fine. Make x within 1/1,000,000th of 1. Okay, we got 2 distances we're talking about. In this example, whatever distance you choose, turns out I can choose the same distance. That's a special thing. It is a coincidence. Not entirely a coincidence, but this is a special example. It has something to do with the slope of this x plus 1 function as a line. But that's the game. You tell me how close you want to make the function to this value, and I'll tell you how close x has to be to that value. That's the idea behind limits. That's almost the formal idea as well. Let's look at an example. Let's go to this particular little example and use that technique we just had. So let's go to the supplemental notes. And we want to evaluate the limit as x approaches 3 of x squared minus 4x plus 3 over x minus 3. A quick question. What happens at x equals 3? It's a limit. It doesn't matter what happens at x equals 3. By the way, if you plug in 3, you get division by 0. You can't plug in 3. Okay, just as well. It doesn't matter what happens at 3 in a limit. Now, it matters in some other things, but when we're doing limits as x approaches 3, doesn't matter at all what happens at 3. Good thing the function's not even defined at 3. Okay. We could write this function f of x. Actually, we could factor the numerator. It's x minus 1 times x minus 3. You need to be up on your factoring and these limits. FOIL this out, indeed, that's what you get. Let's gloss over those little algebra details in the video at least. Oh, look, we got x minus 3 in the numerator and the denominator. Can you cancel those? Well, you know, now you better be careful about that. Yeah, if I write out x is not equal to 3. So we can say f of x equals, bad place for a new line, f of x equals x minus 1 if x is not equal to 3. Yeah, because if f is not equal to 3, whatever number this is, that number is the same and you can cancel them. And the problem is when you get zeros in both places. You can't divide by 0, end of story. So we can write the limit of that rational function as the limit of x minus 1, provided x doesn't equal 3. We just saw it doesn't matter what happens at x equals 3. The functions are different, so what? The limits are the same. This is a question about limits. So when considering a limit as x approaches 3, we can replace this with x minus 1. These are different functions. The only place they're different is at x equals 3, and it doesn't matter what happens at x equals 3. They're different functions, but their limits are the same. So we can write the limit of this equals the limit of the factored version, canceling the x minus 3's. Ooh, I need to write down x doesn't equal 3. I think I did. Whenever you write limit as x approaches 3, you're writing down, as we'll see in the formal definition, you're writing down a whole bunch of stuff. But part of it is x doesn't equal 3. So you might be somewhat bothered with the fact I didn't write x equals 3 down here. Well, I wrote limit though. And part of the implication of that is that x doesn't equal 3. I don't care what happens at 3. I care what happens for x close to 3. Oh, what does x minus 1 get close to when x is close to 3? Gets close to 3 minus 1, it gets close to 2. Purely a coincidence, we've got 2 out for these 2 limit examples that we've done. Funny thing, I can make x minus 1 as close to 2 as you like. In this example, I can't make it equal to if I stay away from 3. And I don't care what happens at 3. Remember, we're choosing x values close to 3, but not equal to 3. Okay, well, that means the limit here is going to be 2, but you never actually get 2 out of this function. So that's an odd behavior of limits. You may hear it said you get closer and closer to 2, but you never get there. Yeah, maybe not as well. That's not a good way to think about limits. It's more involved than that, as we'll elaborate on here shortly. More in the next section, really. Back to the notes. All right, here's a little something I made up. Dr. Bob's anthropomorphic definition of limit. Okay, I'm going to depend on graphs of functions to give me insight on when a limit exists or not. Are you good at graphing? Depending on your pre-calculus background, you might be reasonably good. I mean, you can graph lines. You can graph parabolas. You ought to be able to graph any conic section, in fact. Can you graph polynomials? If you can factor them, you can find intercepts. Maybe you've talked to end behavior models before. It's in pre-calculus. Maybe a detail you didn't get to in pre-calculus, but it's in there. Can you graph rational functions, asymptotes? Maybe if you can do all that, you're pretty good at graphing. You're still not as good as you need to be, and the reason you're not is because you hadn't had calculus. So one of the main applications of calculus in chapter 3 will be to graphing. So this is a little backwards in that we're using graphs to talk about limits. Whereas we're going to use limits to learn things about graphs. So it seems like we're arguing in a circle, but I'm just trying to give you an informal idea of what a limit is. And let's do it in terms of graphs. And you're familiar with graphing things and reading graphs. So we won't worry too much here in the beginning where those graphs came from. Dr. Bob's anthropomorphic definition of limit says that f of x be defined on an open interval about c, except possibly at c itself. Okay, what did that mean? That means the function's defined for input values close to c. Maybe not at c itself, though. I don't care what happens at c. If the graph of y equals f of x tries to pass through the point c comma L, then we say the limit as x approaches c of f of x equals L. Notice it doesn't matter whether it actually passes through the point or not, only that it tries to pass through the point. Okay, that certainly makes no math sense. Um, to put the desires and ambitions of a human on a function. So let's draw some pictures and see what I'm trying to say here. And I think if this will work to give you a good informal idea of what a limit is, or what the graph of a function with a particular limit, what the graph looks like. All right. So of course that's meaningless to say a function has an ambition and tries to do something. That's why I called it the anthropomorphic definition of limit. Let's look at a couple of examples. Actually, let's go back and look at that h function we had before. Now the f and the h function, back when we had the graphs. We said that limit exists. How you feel about this? Look at the graph of that function. It's traveling along, nice straight line. And look at what happens near 1. Near 1, that function is going to try to pass through that point. It fails. The function's undefined at 1 because of that division by 0 thing. But it tried. It tried to pass through that point. If I look what happens, traveling along this straight line, it's going to try to pass through that point. It failed. If I were to come along in the other direction, here we go. This is going to try to pass through that point. So there's a single point the function's trying to pass through. And the limit existed. In fact, the limit as x approaches 1 of f of x equals 2, because it tried to pass through the point 1, comma 2. How about this one over here? It's trying to pass through a point. Yeah, it's trying to pass through that point right there. By the way, it succeeds. Whether I come from one side or the other, this function tries to pass through that point. That's all that matters, according to my definition. It tried to pass through the point. Okay, then the limit of that function as x approaches 1 is 2 as well, because it tried to pass through the point 1, comma 2. Well, they both tried to pass through the point 1, comma 2. Okay, then the limit as x approaches 1 of both of them is 2. One succeeded, one failed. Doesn't matter if we're talking about limits. If we're talking about some other stuff that matters, these are not, well, the one on the left is not a continuous function. That's a story for a different section. They both tried to pass through the point 1, comma 2. All right, then the limit as x approaches 1 of either function is 2. One succeeded, one failed. Irrelevant whether they succeed or fail to the existence of a limit. Relevant to some other stuff, but not to limits. Now let's look at a couple of other functions. We're going to look at f of x equals x, the identity function, the line with slope 1 that passes through the origin, and the function g of x equals a constant. And we're going to observe what happens for an input value of c. Let's talk about a limit as x approaches c for these two functions. Okay, just happen to have a graph of them here. If I make it big enough to see the conversation and the graph, it's going to be too small. All right, here's the f of x equals x function. What's happening at c? Does it try to pass through a point? Yeah, straight line, tries to pass through that point right there. Input is c, output is c, the function is y equals x. So if we input a c, we get out a c, and the function tries to pass through that point. So the limit as x approaches c of this function equals that value. X approaches along the x-axis, and the limit value is a function value, so you read that off of the y-axis. So these c's play different roles. This plays the role of an x approaching c, and this plays the role of a limit value. That function, it tries to pass through this point, don't it? Does it succeed or fail? It doesn't matter if you're asked a limit question. It tried to pass through that point. Yeah, it succeeded, but that doesn't matter for a limit question. How about the g of x equals a constant? Straight line as well, horizontal line. I plug x in, we get k out. I plug anything in, we get k out. It's a constant function. Does the graph try to pass through this point? Yeah. Okay, then the limit, and this is the point c comma k, then the limit as x approaches c of this function is k. To make sense, it's a constant function, constant k. Did it succeed in passing through the point? Well, that doesn't matter. if it's a limit question. And it is a limit question. It did, but that's irrelevant to the limit conversation. Okay, and that's what the words explain up here about trying to pass through the point CC, trying to pass through the point CK. Then respectively, the limits of those two functions are C and K, as just described. Okay, let's look at, this is a little harder to explain, and this is an incomplete conversation as well. So when the limit exists, I know what the graph looks like. When it looks like, well, I got some convenient ones here. So I guess we are talking more about limits existing. We'll look at what happens when limits don't exist here shortly. Here's the graph of three functions. I claim for each of these, the limit exists. Okay, let's just go through them verbally here in the video. I'll leave it to you to read the notes, then I can make the pictures bigger. Okay, three functions, f of x, g of x, and h of x. Same f of x and g of x, h of x that we had before. So that the first one and the last one, we've seen these before. Here's a new one. And I want to analyze these in terms of trying to pass through points. We've done this already a couple of times. Here's a graph. Limit as x approaches 1 of this function is 2. Because look at the graph, it tried to pass through that point there. It failed, but that's not relevant to a limit conversation, is it? Tried to pass through the point 1, 2, then the limit as x approaches 1 of this function is 2, because it tried to pass through the point 1, 2. How about this one? It's the same story. It's trying to pass through this point here, ain't it? It's trying to pass through this one. Okay, then the limit as x approaches 1 of this function, piecewise defined, is 2. Same reason this one was 2. It tried to pass through the point 1, 2. Did it? No. In fact, when I plug 1 into this function, looks like we get 1 out. It's a piecewise defined function like that. Does that change anything? Doesn't change anything related to a limit conversation because I don't care what happens at 1. That doesn't affect limits, what happens at 1. What does happen at 1? Doesn't matter for limit, but I plug 1 in, I get 1 out. It's the 0.11. But that doesn't have anything to do with the limit. It has nothing to do with the limit. The function tried to pass through that point. That's the limit. And we've done this one before. The function tries to pass through that point. By the way, it succeeds, but irrelevant to a limit conversation. It's the 0.12. The limit for all three of these functions as x approaches 1 is 2, because all three of these functions tried to pass through the point 1, 2, 1, 2, 1, 2, 1, 2. End of story as far as limits go. Some additional stuff to help you along. This one failed to pass through the point. This one failed to pass through the point, and this one succeeded in passing through the point. Yeah, well, whatever. Doesn't matter if we're talking limits, but that is their behavior at x equals 1. This one isn't even defined at x equals 1, yet the limit still exists. This one is defined at x equals 1. Its value at 1 is 1 because of the existence of that point right there, but that has nothing to do with the limit. This has everything to do with the limit. It tried to pass through this point. Then that determines the limit as 2. Oh, by the way, I plug in 1 and I get out something else. Doesn't matter what happens at 1. Don't plug 1 in if you're taking a limit. If it were only so easy. Over here, if I plug in 1, well, it doesn't matter for the limit, but this one is defined at 1 as well, and actually the function value equals the limit value. Doesn't matter for the limit, but that's what's happening with this one. So there's three kind of different pictures in terms of what happens when a limit exists. So if you have a graph of a function, the limit exists if the picture looks like one of these three things. Okay, it may not be a graph that's a line. It might be something a little more wiggly, but it's either going to have a hole punched in it at a little point that it tries to pass through, have a hole punched in it at a point it tries to pass through. This is irrelevant. Or it tries to pass through a point and it does, and there's no hole. But in each of these three pictures, the function tries to pass through a point. It succeeds in one, it fails in two. This is kind of some weird little behavior over here as well. But all three of them have a limit as x approaches 1 of 2 because the function tried to pass through the point 1, 2 in all three cases. So when limits exist, the pictures look like this, maybe like this, or maybe like this. All right, now let's look at, and this is a little more awkward to explain, all right, what happens when a limit doesn't exist? Let's look at some pictures. They won't look like those pictures we just saw is what happens. Here's in figure 210 as a graph of three functions. We argue that the limit as x approaches 0, so c equals 0 in these, does not exist for any three of these. There's the verbiage. Let me magnify the pictures and let's talk about the pictures. Okay, we want to know what happens for x close to 0 but not equal to 0. By the way, can you tell it's blue? They've drawn a blue line on top of the negative x-axis, so the function's actually 0 over here. At 0, it jumps up to 1, and then it takes on the value 1. Its piecewise defined function is given there. This function at 0 is 0 because there's a little blue point right there. This one is 0 for the negative input values as well, just like the first one over here. And at 0, the function is 0, as is given in the piecewise definition. Okay, well, these don't look like what we had upstairs near 0, so these limits don't exist. Think in terms of input values. If I input x values close to 0 but less than 0, what are the output values here? Well, there's 0. But that was inputting values close to 0 and negative. What if I input values close to 0 and positive? Well, then the function value is up here at 1. So if I input values close to 0, you can't tell me what the output value is close to. Well, you can give me a list. It's close to either 0 or 1. That ain't how limits work. You need to give me a single number that function's close to if I give you inputs that are close to 0, and you can't. One side it's one thing, the other side it's something else. We'll talk about one-sided limits in 2 or 3 sections down the road, but not now. It is not trying to pass through a single point. From this side, it's trying to pass through that point. From the other side, it's trying to pass through that point. There's not a single point it's trying to pass through. It's got to be the same one from both sides. We just have to have a little hole punched in the graph, or not punched in the graph. Nice continuous function, if the limit exists. So limit doesn't exist. It doesn't look like just a little function with a hole punched in it or not punched in it. There's not a single point it's trying to pass through. Here it's even weirder. Here, if I plug in little negative numbers, I get out huge negative numbers. Will make sense out of the following words in the not too distant future. It's in chapter 2. The function goes to infinity, sorry, goes to negative infinity when I put in x values close to 0 and negative. When I put in x values close to 0 and positive, it goes to positive infinity. We'll put meaning on this. There is no at infinity. Buzz Lightyear was way off. There is no to infinity and there's no beyond. Infinity's not a number. But we'll put meaning on the infinity symbol. It'll be a limit, it turns out. But this isn't trying to pass through some particular point. It takes off unbounded upwards from this side. It takes off unbounded downwards from the negative side. At 0, well, it doesn't matter. We were talking limits. By the way, at 0, it is 0, but irrelevant. There's not a single point the graph's trying to pass through. So the limit doesn't exist. And even more exotic, okay, we got 0 over here. If I plug in little negative numbers, we're always getting zeros out. Output's always 0. It's a constant of 0. See, that's how that piece is defined. So coming in from this side is trying to pass through this point. Does it do the same thing from the other side? So we're taking a sine 1 over x function. So here's what that sine function, not sine x, sine 1 over x. So when x gets close to 0, 1 over x grows rapidly. And so the sine function starts to oscillate like crazy. So they've drawn it oscillating faster and faster Then they just change it to dotted lines. So the idea is that it oscillates between -1 and 1 infinitely many times on the interval from 0 to any positive number. So it's oscillating like crazy between -1 and 1. It's still a function, satisfies the vertical line test, but it oscillates an infinite number of times. Is there a single point this gets close to, or a single point it tries to pass through? No. From the left, it's fine. From the right side, from the positive side, it's all this infinite oscillation stuff. It gets close to the point 0, 1, that point right there. Sometimes, when it doesn't stay close, it wanders away. It gets close to the point -1, 0 for some other times. Actually, it gets close to every point along the y-axis between -1 and 1. But it doesn't stay close. There's not a single point the function tries to pass through. The picture doesn't look like the ones we looked at before. So the limit as x approaches 0 doesn't exist. So here's 3 types of examples when limits don't exist. When we define continuity, we'll talk about a jump discontinuity is what we have here. Of course, this has a vertical asymptote at 0, and this is probably something kind of new to you. This represents a discontinuity as well. Let's just leave it at that. All right, so let's do an example, and let's use Dr. Bob's anthropomorphic definition to, based on a graph, see if a limit exists. Remember, when the limit exists, say the limit as x approaches c of f of x equals L, my anthropomorphic definition says the graph of y equals f of x tries to pass through the point CL. C is what x approaches, L is what the function approaches. Okay, so let's look at exercise 2.2.2. 2.2.2, there we go, where they give you a graph and they ask you about some limits. Okay, here's the graph of the function. They ask you for a limit, just our luck, they've written it in terms of t's instead of x's, well, whatever, it's a dummy variable. And they want to know the limit as t approaches -2 of f of t, t approaches -1 of f of t, t approaches 0 of f of t, and with a little typo there, should read t approaches -0.5 of f of t. All right, well, limit questions at this stage, and it'll get more complicated, but at this stage, I'm just looking to see if the graph tries to pass through a point. And I'll talk about whether it succeeds or fails, although that's irrelevant to the limit question. All right, limit as t approaches -2 of f of t. Is there a point that the graph tries to pass through when t approaches -2? You know, we travel along for t values getting closer to -2. Tries to pass through that point. The same is true if I come in from the other side. Yeah, it tries to pass through the point -2, 0. Okay, well, if it tries to pass through the point -2, 0, then the limit as t approaches -2 of f of t equals 0. Tries to pass through the point, then that's the limit. So the limit is 0 because the function tries to pass through the point -2, 0. It's the y coordinate of that point that gives the limit value. Secondly, they wanted a limit as t approaches -1. Okay, t equals -1 is here. I go to the graph. Does it try to pass through a point? Yeah, it tries to pass through that point. That's the point -1, -1. Then the limit as t approaches -1 is -1. Tries to pass through the point -1, -1, then that's the limit. Did it succeed? Doesn't matter. In a limit question, it matters in some other questions. By the way, it did succeed. It failed to pass through this point. It succeeded in passing through this point. Whatever, as long as it tried, then the limit exists. Limit as t approaches 0. Okay, so we're approaching 0 now. Oh, that's like that example we were just looking at. Is there a point that the graph tries to pass through? Well, when I come in from the negative side, it looks like it's going to try to pass through this point. When I come in from the positive side, though, it's trying to pass through that point. So there's not a single point that the graph tries to pass through. There's no single point that the graph tries to pass through, so the limit doesn't exist. It'd have to try to pass through a single point like this one did, or this other one did. No, that gap there, limit doesn't exist. Sometimes we get values close to -1, sometimes we get values close to 1. We're not getting values close to a single quantity, so limit doesn't exist. What happens at 0? Okay, it doesn't matter. By the way, at 0, the function takes on the value 0 because it passes through the origin. There's a blue dot there to indicate that. But that has nothing to do with limits. What happens at 0, nothing to do with what the limit as t approaches 0 is, again. Okay, how about t approaching -0.5? This is an odd one, I guess. -0.5, -1/2 would be right about here along the x-axis. We'd look here. Is there a point the function tries to pass through here? Yeah, it'd be the point -0.5, -1. They just didn't put a little blue dot there to indicate so. Well, it's okay. It tried to pass through a point. By the way, it succeeded. Not relevant, I know, but it did. It's a nice little continuous line segment there. Okay, tries to pass through the point -1/2, -1, right about there. Then the limit as t approaches -1/2 of f of t must be -1. Tries to pass through the point -1/2, -0.05, or -0.5, comma -1. Tries to pass through that point, then the y coordinate is the limit, and the limit exists. So there's how we can get limits from graphs. And some of the homework exercises will involve that. Let's look at some limit rules. It's awfully early to be talking about theorems and rules concerning limits when we haven't even formally defined limit. Well, we're going to do it anyhow. We'll justify it later. The next result gives some properties of limits. We'll address the proofs of some of these properties when we have a rigorous definition of limit in the next section. And after section 2.3, you can look at Appendix A4, and there's proofs of some of these things there as well. For now, let's take this as given so we can do some more stuff with limits. I want to do some algebra stuff instead of just having to rely on graphs all the time. So that's why we're doing this now. Let L, M, C, and K be real numbers. Suppose, so this is an if, suppose the limit as x approaches c of f of x equals L, and the limit as x approaches c of g of x equals M. Then we get the following to hold. So, what do you make of the limit as x approaches c of f of x equals L? What do you make of that? I guess a graph of f of x tries to pass through the point c comma L. What do you make of this? The graph of g of x tries to pass through the point c comma M. Do they succeed? Nobody cares. This is a limit conversation. The rules are called the sum rule. It says the limit of f of x plus g of x is the limit of f of x plus the limit of g of x. The book doesn't put these intermediate things in the middle that I've put in here. I think this makes it a little clear. The limit of the sum is the sum of the limits is a quick way to read that. But the book's written it in terms of the L's and the M's over here, and I included those as well. But I think it's cleaner to write out more stuff. You can see what's going on. The difference rule says the limit of f of x minus g of x is the limit of f of x minus the limit of g of x. The limit of the difference is the difference of the limits. So it's very similar to what we had in part 1 there. The constant multiple rule says if we take a limit as x approaches c of constant k times function f of x, that's the same as k times the limit as x approaches c of f of x. You can bring the k outside of the limit process when it's a constant. When it's a constant. Can't do that with variables. But constants can be brought outside of limits. That's the constant multiple rule. Product rule, limit of f of x times g of x is the limit of f of x times the limit of g of x. Limit of the product is the product of the limits. Be very careful in the next one. Quotient rule, says the limit of the quotient is the quotient of the limits. If, I had to put an extra condition in here, if the denominator doesn't have a limit of 0. You can't have 0 in the denominator. So you better be very careful. This is the first one that's required any extra hypotheses. You can't divide by 0, so when you take the limit of a quotient, you better make sure that denominator ain't 0. Otherwise, you can't do this. I'm not saying the limit doesn't exist. We've seen examples where we had limits of 0 in the denominator, yet the limit still existed because we did some cancellation that we justified. So quotient rule says the limit of the quotient is the quotient of the limits if the limit of the denominator is not 0, not equal to 0. Power rule and the root rule deal with exponents. If n is a positive integer, 1, 2, 3, and so forth, we're not allowing 0 to play a role, and we're not using negative exponents just yet. Claim is the limit as x approaches c of f of x to the n power, so we're taking a whole function and raising it to the nth power. Limit of f of x to the n is the same as the limit of f of x, parentheses, to the n. So we've taken the limit inside that raising to the nth power process that's going on. Limit of a function to the nth power is the limit of the function, pause, to the nth power. The parentheses explain it more clearly than the verbiage. And the same kind of thing happens when you take nth roots. If n is a positive integer, like if we were taking square roots or cube roots or so forth, if n is a positive integer, then the limit as x approaches c of the nth root of f of x equals the nth root as the limit as x approaches c of f of x. So we took the limit inside that square root, and there's more conditions on this. If n is even, so you're taking square roots, fourth roots, sixth roots, and so forth, we require f of x to be greater than 0 on some open interval containing c, except possibly for c itself. All right, so of course, except possibly for c itself. I don't care what happens at c. What this is you're avoiding square roots and negatives. You can't take square roots of negatives. You can't take square roots of negatives because I won't let you. You can't divide by 0 up here in part 5 because nobody can divide by 0. You want to take square roots of negatives, come back and see me in a year or two, and we'll do complex variables. We'll do calculus with complex numbers. But for now, no square roots of negatives. You got enough problems. So this hypothesis says avoid negatives when this n parameter is even. For example, when it's 2, you can't take square roots of negatives. If we get square roots of negatives, then we're going to have limits that don't exist because we're only considering real numbers, not complex numbers. If n is odd and you're taking cube roots, now you can take cube roots of negatives all you want. So it's not an issue when n is odd. The textbook states the root rule slightly differently. My statement is, well, all modesty aside, mine's better. In fact, I think you need mine to do some of the problems that are in here if you really want to be picky about details. And that's kind of what I do. But as long as you don't have square roots and negatives, then you're good to go. Can you get a square root of 0? Square root of 0 is 0. Is there anything that prohibits square root of 0? Well, we'll see some examples when we're doing one-sided limits where square root of 0 is kind of an alarm bell, a warning sign. It's not that you can't take the square root of 0, but close to 0, there's negative numbers, and all is close to stuff. That's the problem. You can't take square roots of negatives, and if you get a square root of 0 out by substituting stuff in, remember, things are moving around. Maybe x isn't at 0, but close to 0. Close to 0 is negatives, and there's the problem. So this disclaimer about being non-negative on some open interval containing c, except possibly c itself, that'll take care of the fact that we can deal with square roots as appropriate. The book's way is a little bit weaker, so this is a little better. Let's look at an example, 2.2.52. Okay, 2.2, number 52. Says, whoops, if the limit as x approaches 1 of h of x equals 5, the limit as x approaches 1 of p of x equals 1, the limit as x approaches 1 of r of x equals 2, so each of them are approaching 1. There's 3 different functions, and they give us out the limit values. what's this mean to you? By Dr. Bob's anthropomorphic definition of limits, it tells you they're trying to pass through certain points, if you like. The question here is, name the rules from Theorem 2.1 that are used to accomplish steps A, B, and C in the following calculation. So we've got a limit of square root of 5h of x divided by p of x times 4 minus r of x. All right. They take the limit of this thing and they write it like this. They've got a limit in the numerator and a limit in the denominator. Who says you can do that? Well, that's limit of a quotient is a quotient of the limits. It better make sure you don't get 0 in the denominator, eh? Part A, we use the fact that the limit of the quotient is a quotient of the limits. That was the quotient rule. So they've used the quotient rule in this part, as we stated in the theorem. All right, let's see. They got a square root here. They're doing something with that. Okay, they've taken the limit inside the square root function. That was called the root rule that they've used there. So I've used the root rule on this part to take the limit inside the square root function. The limit of the square root is the square root of the limit. Better make sure they're staying away from 0. They are. Let's not get into it in that much depth though. And here they had a limit of a product, and in the denominator, limit of p of x times 4 minus r of x. They've written it as the limit of the first times the limit of the second. That was limit of the product is the product of the limits. That one was called a product rule. So in part B, we've got a root rule in the numerator and a product rule in the denominator. Okay, let's go to a new slide and explain part C. So how'd they get from here to here? They brought the 5 outside of the limit. You can do that. Constant multiple rule. You can take constants outside of limits. And let's see, the limit as x approaches 1 of 4 minus r of x. They wrote as the limit of the first minus the limit of the second. That's the difference rule. Did they just distribute that limit? No. Distribution is something you do with multiplication. This ain't multiplication. This is limits. It's the difference rule. So there is no distribution in any of this limit stuff. Distribution is something you do with multiplication. We're not multiplying, we're evaluating limits. It behaves in a similar way, but it's the difference rule that we've used there. So let's see, constant multiple rule in the numerator. Yeah, constant multiple rule in the numerator. And rewriting this part of the denominator as this is the difference rule in the denominator. So that explains all those steps. Then, let's see, you know what the limit as x approaches 5 of h of x is, don't you? They told you it was 5. So they've substituted at this stage. Substituted the limit values in, a 5 here. P of x had a limit of 1, so a 1 here. R of x had a limit of 2, so a 2 here. Do the arithmetic, it looks like you get 5/2. But they wanted us justifying the steps they took. There's how you justify them using the theorem we just stated. All right, so one of these days we'll actually evaluate a limit. Okay, let's look at polynomials and illustrate those. I'll tell you what, this is becoming a lengthy video. Let's cut it there, and I'll come back and do the remainder of this section in a second video. Have a nice day. I'll see you soon.